the last lecture, we were talking about a geometric optimality condition. Now, in this lecture, we shall continue our discussion on that geometric optimality condition, and especially we shall talk about a new cone that is called the tangent cone for a constant optimization problem, which will be helpful to find another geometric optimality condition for a constraint optimization problem. If we recall our last lecture, we will find that we were discussing on the last lecture the cone of feasible directions, and after the discussion of cone of feasible directions, we have discussed about an example on the cone of feasible direction, and then it is effectively a cone that you all can verify, and hence it is called a cone of feasible direction. We were discussing the idea of linearizing cone. The linearizing cone is found to be superset of the cone of feasible direction. In order to see that the cone of feasible direction is really a strict subset of linearizing cone occasionally, for that we have given this example where we have seen the cone of feasible direction is really a strict subset of the linearizing cone. Then later on the cone of descent directions was discussed with the help of the cone of feasible direction and cone of descent directions. We have found a geometric necessary optimality condition, and that we call as geometric necessary optimality condition 1. And there we have found that if the point x0 is a local minimizer of a given constraint optimization problem, then the cone of feasible direction and the cone of descent directions at the point x0 is having no common element. And then next we have given one example that this is really a necessary optimality condition. However, it is not always sufficient. Now, towards the end of the last day's lecture, I have asked a question to you. I guess you all have gone through that question. That question is asking you to check whether not only this condition, that the cone of feasible direction and cone of descent direction is having empty intersection at a local minimum point, but also whether you can also have that the linearizing cone and the cone of descent directions is empty at the point x0, which is known to be a local minimizer. But answer of this question is negative. It is not, and for this we will have to give one example. One such example is the following. For this you consider minimize the function fx that is given by minus x1 subject to the constraints that u1x, this function first inequality constraint, is given by x2 plus x1 minus 1 whole cube less than equals to 0. G2x is equal to minus x1 less than equals to 0, and G3x is given by minus x2 less than equals to 0, and the set capital X is the entire R2 plane. Fine. For this example, you will find that you just check that the point x0 is equal to 1 0 is a local minimizer, but you will see that the linearizing cone intersection the cone of descent direction at the point x0 is not equal to null. I put it as a home task. You please verify it. And now here you note that the linearizing cone and the descent direction cone may have non-empty intersection at a local optimum point. Therefore, although the linearizing cone was found from the motivation that if you have a point in the cone of feasible directions, then you take the linear approximation of the binding constraints, and you are getting the linearizing cone. Therefore, what happens is that expression for linearizing cone is readily available to you. Some of you might have come across with the problem from the last test lecture, that how to find the cone of feasible directions. The cone of feasible directions is not easy to find. By not easy to find, I mean an algebraic expression to represent the cone of feasible directions is not an easy task. Although you have defined cone of feasible directions from a geometrical essence, but an algebraic expression for the cone of feasible direction is not easy to find. And knowing this fact, the linearizing cone, which is an extension of the cone of feasible directions, because cone of feasible directions is always a subset of the linearizing cone. The linearizing cone is, although easy to find its algebraic expression, but the linearizing cone and the descent direction cone, they may not have empty intersection at a local minimum. And therefore, as we are endeavoring to find optimality conditions, and towards this we have found that this is essentially an optimality condition, the geometric optimality condition 1, but the cone of feasible direction is not easy to execute. And knowing this fact, we were trying to identify an algebraic expression for the cone of feasible direction, and for that we had to define a new type of cone called the linearizing cone. Fine. But ultimately what is happening, the linearizing cone and the descent direction cone at a local minimum may have non-empty intersection, and therefore although CL has a nice algebraic expression, but CL is not useful for identifying a necessary optimality condition. And therefore in the next, what we will endeavor is to extend in another possible way the cone of feasible directions, and towards this we will define a new type of cone that is called as tangent cone. There is also another motivation behind defining the tangent cone, is the following. You note that the cone of feasible directions although gives a very nice geometric optimality condition, but cone of feasible direction is not only difficult to execute, but also what happens, the cone of feasible directions might be containing only the null vector in many of the practical cases. For instance, if the feasible region is just a curve like this in the R2 plane, then in this case you note that you consider any particular point in this curve, then you note that the feasible direction cone contains only the null vector. There is no non-null vector that is contained in the cone of feasible direction, and therefore if the feasible region is a curved surface, like in R2 this is a curve, or in R3 let's suppose you have another curve like this, let's suppose a surface like this. So you have a surface like this in the R3 space, and this is a curved surface that constitutes the feasible region of the problem. Then in that case you will find that you don't have any non-null direction which is the cone of feasible direction. If the cone of feasible direction does not contain quite a few directions, then to develop an algorithm, a descent algorithm rather. What do we mean by descent algorithm? By descent algorithm, we mean that the general structure of an optimization algorithm, that you start your algorithm from a given initial point, then you find a descent direction, then you keep on moving in this manner. Fine. So this is called a descent method, that at every iterate xk you are finding a descent direction and you are keep on moving. And here you note that if we are starting to find an algorithm, a decent algorithm, then in that case we note that for every iterate xk you need to have a descent direction which is non-null direction. And if your cone of feasible direction contains only the null vector, then inside the cone of feasible direction you cannot run a decent algorithm. You cannot develop a decent algorithm. To develop a decent algorithm in a given set, you need to have quite a few feasible directions in the constraint set of the problem. And as the cone of feasible direction in many of the cases, when your constraint set is a curved surface, in that case you will find that the cone of feasible direction is having only the null vector, the singleton set. And therefore we need to somehow extend the cone of feasible direction to include quite a few directions, and those directions lead to a feasible point in the region. For instance, at this point, instead of just considering the cone of feasible direction the way that we have defined, if we define a set such that you include in that set all those directions such that those directions are giving along the directions, if we move, then you are going to get at least one of the feasible point, then you note that you have now a ample number of directions in that set, and such a set is eventually called as a tangent set. With the help of this idea that you move along the direction such that on those directions you have a feasible point, you now accumulate all such directions which are leading to a feasible point. May not be all the points in that direction are feasible, which is required in the cone of feasible directions, but you consider those directions which contain at least one feasible point, then you just collect those directions and you define a set, and that set obviously will include several possible non-null directions and they include feasible region. Fine, anyway, and therefore if we extend the cone of feasible direction in that way, we can devise efficiently descent algorithm, and it is possible because of the fact that in that extended cone, an extension of the cone of feasible direction, in that cone you will have quite a few non-null direction, and that is required for a descent algorithm to devise. Anyway, now next we will try to discuss about the idea of a new cone that is called a tangent cone, and we will see that that tangent cone is an extension of the cone of feasible directions. Now for tangent cone, the idea is as follows. Now at first let us recall our idea of tangent from our high school level. How did we define tangent on a curve? Then later on we will extend this idea for tangent on a set, because here we are trying to find tangent cone for a feasible region, for a feasible set of an optimization problem. So we are now trying to extend the idea of our high school level of tangent on a curve. We'll extend it for tangent on a given set. Well, so let's suppose I have a curve like this and I want to find the tangent at this point. Let's suppose this point is the position of P. And how did we define tangent at the point P? It is as follows. You consider several chords. That means you are considering several points Q1, Q2, Q3 and so on, and this Q1, Q2, Q3 are in the local neighborhood of the point P. That means they are very close to the point P, and then you keep on finding the chords PQ1, PQ2 and then PQ3, and slowly as Qn tends to P, you are reaching to this direction. Fine, and this direction is called a tangent direction. That means what you are doing, this is my origin. Let's suppose the position vector of the vector P is, let's suppose, x, then PQ for this scenario, that you are considering all these directions PQ1, PQ2, then PQ3 and so on. Ultimately this PQ3, PQN converges to the direction of PQ, and PQ has direction, let's suppose this is the direction OI, right? And therefore we say PQ vector as a tangent to the curve that I have drawn here. If you find a sequence Qn on the curve such that Qn converges to P and PQN converges to PQ. Fine. Then we say the vector PQ a tangent. Similarly, on the left hand side also you will be able to find a tangent. Anyway, I'm just considering on the right hand side. The left hand side will be equivalent. Anyway, so such a vector PQ is called a tangent on the curve. Now, if I algebraically try to present it, it is as follows. Let's suppose Q1 has position vector x1, Q2 has position vector x2, Q3 has x3, and so on. So this scenario is equivalent of saying that the vector PQ is a tangent on the curve if you have that a sequence xn on the set. Let's suppose this is my set. I am just denoting this by m, set of all possible xy's such that y equals to fx. Now if there exists a sequence xn where xn points are lying on the curve, that means you have xn corresponding to xn fxn. So xn fxn is belonging to m. So there exists a sequence xn such that xn converges to the point x, the position vector x, and this will imply that pqn has the position vector xn minus x that converges to y. Fine. This is what it is saying. The position vector of xn minus x that converges to y. You might feel here that as xn converges to x, you might have xn minus x converges to 0. It is not really the fact. This is due to the fact that you are not just moving from xn to x, but what you are doing is that here pqn is a chord to the curve y equals to fx. That restriction makes you not to have xn minus x converges to 0. Or rather, it will be much more interesting to observe that we know that not only y but also this is also a tangent direction. Let me draw with a different color. If I would have considered a bigger length, you know that this is also a tangent, that let's suppose lambda times y, where lambda is bigger than 1. Then you know that this is also a tangent direction. Fine. And therefore if I just keep on extending or squeezing the position vector y, that will still be a tangent direction, and therefore keep our attention only on the directions that this xn minus x is converging to y direction wise. That means the direction x minus x converges to the direction y. It is not that just xn minus x converges to y. So here xn minus x, so here we will just consider here on the top of this arrow is capital M. That means your points xn's are in the set M, and on the set M your xn minus x, you consider all these chord directions, they are converging to y. Now here as y is a tangent, lambda y is also going to be a tangent. For the same vectors, same sequence xn that I have drawn here, q1, q2, q3 and so on, this direction will lead to y, not lambda y, right? But we know that either this blue arrow or this orange arrow, both of them are tangents, right? Now in order to find a general definition for tangent, because here this blue arrow is also a tangent, orange arrow is also a tangent, a bigger arrow line on the same direction is also a tangent, and therefore what we do is, in order to resolve this anomaly, what we consider is, we consider to focus on only unit vector as the directions. So we'll just identify the unit direction of y. Then we note that we are just normalizing the direction y. So this y of length 1 will give us this much, this arrow, and for lambda y also we know that the same arrow, this violet arrow is same for lambda y also. The normalized direction for y, the normalized direction for lambda y, normalized direction for other lambda value into y is the same direction, this violet direction. And therefore what we are considering is, at the point P you consider a unit circle and then in the unit circle you map all the directions. In this unit circle you map all the directions that you consider here. Xn minus x, that has to be mapped on the unit circle. That means you are considering this normalized vector, and this normalized vector is converging to y divided by norm y. Now you can consider either the blue arrow as the tangent vector, or you consider the orange arrow as the tangent vector. They eventually will be the same direction, right? And therefore we define tangent on a set in this manner. However, this convergence is only on the set M. This is not the usual convergence. In the usual sense, xn converges to x will imply xn minus x converging to 0. However, as you are restricting your attention only your xn to be lying on the set M, therefore we are putting here up of the arrow the set M. Anyway, so now let us define tangent on a set. This is tangent on a curve. In the description of this tangent direction, I should have used some other notation than y. You should not be confused with the y that I have taken in capital M and the y that I have taken here to denote the vector PQ. Fine. Now let us go for defining tangent direction at a point on a given set. The definition that we have described for tangent direction for a curve can be extended to define tangent direction at a point on a given set. It is in the following manner that you consider a set. I'm just considering the same curve, but from the same curve we will just consider a set so that our understanding will be very neat, clear before us, because we have understood tangent vector on the boundary of this region. Fine. Now let me consider this set, and on this set I am trying to find a tangent vector. Let me pick up this boundary point. You could also take some other point inside the set, and let me at first consider the boundary point. In the boundary point, note that what are the possible directions, those can be declared as a tangent. In the earlier case, when you had only the boundary of the curve, we note that you had y by norm y, and not only y by norm y, but also minus y by norm y is also a tangent vector, right? Because on the left hand side you have the another direction. On the left hand side also you could take this vector, this is also a tangent direction, right? From the left hand side you can find it. So not only y by norm y but also minus y by norm y, that is also a tangent vector to the set. Now here we know that for this scenario, when I have the feasible region contains all of these points off of the surface of y equals to fx, and also it includes the boundary. This is my set, and in this case I am trying to find the tangent at this point on the set. How do you find the tangent? It is as follows. The definition is the same, that I say a vector y a tangent on the set M. This M can be any set. I'm not restricting M to be a curve. On the set M, if either y is a null vector or there exists a sequence xk in M, that means all the points xk's are in M, such that xk converges to x and xn minus x divided by norm of xn minus x is converging to vector y divided by, right? This is your definition, or y is called tangent at x naught. So here you start with x naught taking from the set M, and M obviously is a non-empty set you are considering because x naught is belonging to capital M. So here we are letting an element x naught. So at x naught we say the vector y as a tangent if this is happening. That you have found one sequence xk inside the set such that xk converges to x naught and xn minus x naught divided by its norm converges to y by norm of y. And this will eventually take care about that the unitized vector is converging to the unitized vector. So this will take care about this m. This is due to the fact that if you have taken here m, but here we know that in this step you need to take m, but in the latter step you don't need to. Even if you don't take m, that doesn't matter, because here you know that this xn minus x eventually is not in the set, and you have to take care about m. You have to take care about m, take care about y and lambda y being tangent. We have unitized the vectors. Now here you note that we consider the point x naught. Then we have several sequences on the set M that can converge to the point x naught. For instance, I can take this sequence on the set, and this sequence will lead to converging to the point x naught. I could equally take the following sequence, interestingly, that I can just take this curve inside the set M, and I can take a point in collection of points, a sequence I can construct on this curve, and this also will lead to the point x naught. Fine. I could similarly take another curve over here, and I take the points this, 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 this. So in this way, you construct a sequence on the curve, on this pink curve, and you will converge to the point x naught. Now let me focus on this first sequence, then here the second sequence, then here the third sequence. So you note that all these sequences, sequence number 1, sequence number 2, sequence number 3, all of them are converging to the point x naught, and all these sequences are inside the set M. There is no doubt, right? Now we note that for the first set you will find that this is a tangent direction. For the second set you will find that this is a tangent direction. The third set, it is a tangent direction. Those are effectively the tangent to the curve, respectively this blue curve, then this green curve, and then this violet curve, right? So all these three directions are tangent directions, and effectively for this set you will be able to find that all the vectors in this region, all the vectors in this region, that means above of this line, above of this orange line, are tangent vectors. Fine. Now let me consider another few examples and execute the tangent vectors, and after that we will find another equivalent definition which is usually used as the characterization of the tangent cone. That is another just definition taken by several textbooks. That particular definition which is equivalent to this, that we will prove. That particular definition essentially benefits us on deriving optimality conditions. Anyway, so here the idea neatly is the following. A vector y is a tangent at a given point x naught in the set M if there exists a sequence xk in the set M such that the normalized direction xn minus x naught converges to the normalized direction of y. Fine. So this is what the definition of a tangent. And tangent cone is defined by the collection of all the tangents. We denote it by ct x naught. This is then defined by set of all y's in Rn such that there exists a sequence xk in M and it converges to x naught, and xn minus x naught divided by norm of xn minus x naught converge. Well, and this will include also y as origin, because you know that you just consider the constant sequence x naught. In that case, what will happen? So here you need to include the origin as well. Fine. So this is your tangent code. Now, before giving several examples, let me give you the equivalent definition by a theorem. That, that theorem says that a vector y is tangent at x naught on M if and only if there exists two sequences xk in M and alpha k, a real sequence that converges towards 0 from right, such that 1 by alpha k times xk minus x naught converges to y. Well, so let us prove this result. The proof will be as follows. For the forward part, so we are assuming let xk be a sequence in M, and alpha k is a decreasing sequence, decrease to 0, such that xk converges to x naught, and 1 by alpha k times xk minus x naught is converging to y. We assume this, then we'll prove that this is happening, that normalized direction is converging to normalized y. Okay, so how do we prove this? The proof will be as follows. Here it will be k, not n. Well, now from here we know that then we'll have your norm of xk minus x naught, sorry, the left hand side, numerator you don't have any norm, divided by norm of xk minus x naught, that we have to prove converging to y by norm y, right? This is just a matter of manipulation. This manipulation is done in the following way. This is equal to, we note that as alpha k is positive, therefore you have here xk minus x naught divided by alpha k whole divided by norm of xk minus x naught divided by alpha, right? And these converges to, you note that the numerator is converging to y, and once the numerator converges to y, the denominator obviously converging to y. This is due to the continuity of the function norm, and therefore this implies y is a tangent, right? That is the definition of tangency of y at x naught on the set M. Now for the reverse part, it is given that xk a sequence in M such that xk converges to x naught and xk minus x naught divided by norm of xk minus x naught is converging to y by norm y. Now from here we have to prove that there exists a sequence, positive sequence converging to 0, and also this, that 1 by alpha k times xk minus x naught converging to y. This is again a matter of manipulation, that you take alpha k to be norm of xk minus x naught divided by your norm y. If I am taking this, then obviously your alpha k is positive and tends to 0. And also you have the following: 1 by alpha k times xk minus x naught. This is equal to xk minus x naught divided by norm of xk minus. This converges to y. So this converges to y by norm y into norm y, and which is equals to y. That is what you wanted to prove. So equivalent definition for tangency of the vector y at the point x naught on the set M is the following: that there exists one xn in M and alpha k positive sequence that converges to 0, such that this is happening, that 1 by alpha k times xk minus x naught converges to y. And I suggest you to listen this video 2 to 3 times, because tangent cone is very crucial and difficult to understand rather. Several textbook will just give the theorem as the definition, but essence of the geometrical essence is rarely found. In order to find another nice geometrical fact for the tangent cone, I suggest you to follow the book by Bartesecus, page number 249, and the title of the book is Convex Optimization and Applications. Fine, this is the title of the book. This has published in Athena Publisher and written by great optimizer Bartesecus. Now, here you note that out of all these three definitions of tangent cone, the linearizing cone, the cone of visible directions, you note that the cone of visible direction is defined geometrically. The tangent cone is also defined geometrically. Actually, although you have an algebraic expression over here, but geometrically it is defined. That the idea of tangent on a curve is taken up, then from that the idea is generalized. But if I give you the expression of M in terms of several inequalities like g1x, g2x less than equals to 0, it is very difficult to find the expression for this tangent cone in terms of g1, g2. So although you have a characterization result, Ct is defined by this. But in terms of g1, g2, this algebraic expression for the tangent is very difficult to find. And what is most interesting is that in many optimization theory, when you will use the tangent cone, you just need this definition. And from this definition itself, although you do not have a closed form expression in terms of the expression of g1 and g2, but still this definition is enough to derive several optimization conditions. And we'll find now optimality condition with the help of the tangent cone. Similar is the fact for the cone of visible directions. And for the cone of visible directions, that is also defined in the same way, that you take a point x naught and we call a direction feasible direction if you have that inside the feasible region M you have at least a length which is feasible in nature, and but you don't have any algebraic expression for the cone of feasible directions. That's why we have derived the idea of the linearizing cone. But although linearizing cone can be presented in an algebraic manner, that means with the help of the expressions of the constant functions, the linearizing cone can be easily identified. But we have seen that linearizing cone is not helpful to find an optimality condition. We have seen one such example at the starting of this lecture, that at an optimum solution of a minimization problem, the linearizing cone and the cone of descent directions may not have empty intersection. And thus, we tried to extend the notion of feasible directions in some other way, and we were trying to talk about the notion of tangent cone. Now, let us try to identify whether the tangent cone can be helpful to find an optimality condition with the help of the cone of descent directions. We have an affirmative answer for this, and towards this, at first we shall get to know a result that the tangent cone lies in between the sets of the cone of feasible directions and the linearizing cone, and then we shall get to know a geometric optimality condition with the help of the tangent cone. So towards this, at first let us get to know that the tangent cone effectively is a superset of the cone of feasible directions. A theorem that interrelates the cone of feasible directions at a point x naught and the tangent cone at the point x naught and the linearizing cone at the point x naught. Fine. And here, instead of the set, the closure of the set can also be taken. Now here, although we have this relationship, sometimes you will find that they are equal, but may not be always. For this, we have to give several examples that cone of feasible direction can be strictly subset of tangent cone. Tangent cone can be strictly subset of the linearizing cone. Maybe equality is also happening. Several examples I will provide. But before that, let me be clear about tangent cone for several feasible region. Now, let me give you the location where this proof can be found. The proof for this can be found from the page number 50 of the book by Sun and One. Now, let me give you quite a few examples related to the tangent cone. First example, we consider the set M1 given by x1, x2 belonging to R2 such that x1 greater than equals to 0, x2 is lying in between x1 square and x1 square times x1 minus. We'll just graph out the figure, and from the graph itself we'll just sense what is the tangent cone, because the definition of tangent cone will not help you out to find the tangent cone, and therefore we'll just draw out the figure, and from the figure we will try to visualize what can be the tangent cone. Now for this set, if you try to draw out the region of capital M, you will find the following. This is my x1 axis, this is x2 axis. Now here x1 is greater than equals to 0, only on the right side of the x1 axis you have now x2 equals to x1 square is the parabola, this parabola whose tangent is x1 axis, and x2 equals to x1 square into x1 minus 1 will be this curve. For both the curves, x1 axis is the tangent, and therefore whatsoever curve you can think of inside this region passing through 0 0, that will have the tangent x1 axis. So let me take quite a few points. Let me take your x0 is equal to 0 0. In this case, your tangent cone is just this set. Starting from origin, you have this right side. Only this is the tangent cone, no other point. So for this, your tangent cone CT x0 on the set M is set of all directions D1, D2 such that your D2 is equal to 0. D2 equals to 0, but also you will have D1 greater than equals to 0. Fine. Now next example let me take. For let's suppose I want to find the tangent cone at 1 0. Then at this point we know that the tangent cone is obviously, here is the tangent to the curve. This is the tangent, and any point above this line is tangent to the set M, and accordingly for the point x0 is equal to the point 1 0, you have this set D1, D2 such that the equation of the tangent is d2 is equal to d1 minus 1. Now for x naught equals to 2, 4, here you note that the tangent cone will be this tangent and this tangent. This region will be the tangent cone. Here outer is tangent to the outer curve, and this inner line, this line is tangent to the parabola. Fine, this is your tangent cone. Sorry, here this is better than equal. Fine, and here the tangent cone, this C2 x naught. I have given you enough hint. Can you be able to find what is the expression? Here you note that this cone is starting from origin, because we have just taken origin as the point x naught. However, in the second point we have taken the point 1 0, and at 1 0 I have drawn this figure d2 greater than equals to d1, and but d2 greater than equals to d1, this tangent cone is eventually located over here, that in the d1 d2 plane. We have to draw this figure in the d1 d2 plane, right? d1 d2, we have to draw this figure in the d1 d2 plane. In the d1 d2 plane, this is also in the d1 d2 plane. In the d1 d2 plane, this figure will give us this, and in the d1 d2 plane, this figure will give us this arrow marks, and for in the d1 d2 plane, for the point 24, you will have this as the cone, and your cone is defined in the d1 d2 plane only. The cone is not defined in the x1 x2 plane. Now in order to visualize it appropriately, you are shifting your cone at the concerned point x0. So you are shifting the origin of d1 d2 to the point x0, and then you are observing the figure of the tangent cone, and that will give a quick visualization that tangent cone essentially gives us the tangents to the curve related to the definition of the set M1. Fine. Now next ahead, let me consider another few examples. Here I take off this instance, that consider M2 is equal to the set x1 x2 belonging to R2, such that minus x1 cube plus x2 is less than equals to 0, minus x2 less than equals to 0. Here let me mention you, because for this tangent cone definition you need to read a textbook, although in optimization textbooks are very difficult to find, but at least the book by Forst and Hoffman contains several examples on the tangent cone. And for all these cone definitions and the notations, the linearizing cone, the tangent cone, the cone of visible directions, cone of distant directions, all the notations I am taking up from the book of Forst and Hoffman, and there are several examples are there. You can have a look on them in order to better sense what is the essence, geometrical essence of all these cones that I am defining here. Now consider this set M2 and take the point x0 is equal to the origin. And here let us try to find what is the tangent cone. Let me draw out the figure. Here is your x2 axis, here is your x1 axis. x2 is equals to x1 cube is this figure, and x1 axis is the tangent to this. X1 cube is bigger than x2, so this is the region with minus x1 less than equal to 0. For this region, what is your tangent cone at the point origin? At the point origin, we know that the tangent cone consists of the set. Here the tangent cone obviously to the boundary curve is the x1 axis, and to the x2 axis, the boundary, it is this, right, tangent. And therefore all the points in the first quadrant gives us the tangent cone. So here the tangent cone at the point x0 is set of all directions d1 d2 such that d1 is greater than equals to 0, d2 is greater than, and let me consider another set. Here you consider m2 is equal to, here you consider minus x1 cube plus x2. Oh, sorry, I have drawn the figure for greater than equals to, not less than equals to. Sorry, here it is greater than equals to. X2 is bigger than the curve x1 cube. So here greater than equals to 0, to consider minus x1 less than equals to 0, minus x2 is less than equals to, and you take the same point x not equals to 0. And for this, we note that the sets are different. M2 and M3, M2 and M3, these two sets are different. Their presentation is different. However, the sets are effectively identical. Their presentation is different. Algebraic presentation is different, but the sets are the same. That your, this is the set M3 again, and here is also the tangent cone is at the point 0 0 is the same set d1 d2 such that d1 is greater than equals to 0, d2 is greater than equals to 0. And therefore what we can conclude over here is that the tangent cone does not depend on the algebraic presentation of the set capital M. Fine, but that is not the fact of the linearizing cone. Linearizing cone depends on the algebraic presentation. Here you can quickly find that linearizing cone for the set M2 and the linearizing cone for the set M3, they are different. However, the tangent cones are same because their geometry is same. Geometrically M2, M3, they are identical, and therefore tangent cone definition as it is defined from the geometrical essence, tangent cone depends on the geometry of the set, not the algebraic expression of the set. Well, now let me put a note here that, rather let me put a note over here that would be more appropriate, that you note the following, that will be interesting to remember, that we know that the cone of feasible direction, the cone of the tangent cone and the linearizing cone, all of the cones are defined in such a way that origins are included in the set. You have the origin belonging to the cone of feasible direction, you have origin belonging to the tangent cone, you have origin belonging to the linearizing cone, but origin does not belong to the cone of descent directions. Fine. Anyway, now let me give you just quickly hint you as an example that the tangent cone is strictly subset of the linearizing cone. For this, you consider the set M2 given by this x1, x2 such that x1 cube plus x2 is less than equals to 0, minus x2 is less than equals to 0, and you take the point x0 equals to the origin, and here you will find that a strict subset is coming out. Tangent cone is a strict subset of the linearizing cone. And for ct is equal to cl, for that you consider the set m3. Here you have the same set although, but with a different algebraic expression, minus x1 cube plus x2 is less than equal to 0, minus x2 less than equals to 0, minus x1 less than equals to 0. For this set, you will find that the linearizing cone and the tangent cones are same, but another example where you will have the cone of feasible direction is a subset of the tangent cone. For this, you take the set M given by the periphery of the unit circle, x1 square plus x2 square is equal to 1, and you take the point x0 is equal to 1 0. I'm putting all this as home task, and you please verify all of them. On the next day, then I will give you the geometric necessary optimality condition 2, and from where the Karus-Kuntakar necessary optimality condition will be derived. Once it is finished, then we will move towards the Karus-Kuntakar sufficient optimality condition. At first, the first order KKT necessary and sufficient condition, then the second order necessary and sufficient Karus-Kuntakar condition will be discussed. Then later on, the idea of constraint qualification will be discussed in detail. These things are all very much mathematical, but as this course is floated from the mathematics department, unless we have a mathematical flavor, unless we have a detailed mathematical understanding on the topic of optimization, you know, just the methods on optimization, that is not really interesting. Methods are knives that they can just solve problems, but unless you know nitty-gritty of the methods, the convergence of the methods, how the methods are being derived, you might not be able to derive a new method. And you are all youngsters with bright minds. It is expected from you all that after attending several courses on optimization, you will derive someday some optimization technique which can better solve several practical optimization problems. Well, so on the next day, we will have then the topic of necessary geometric optimality condition, necessary geometrical optimality condition 2. Then we'll have the KKT necessary and sufficient optimality condition, both first order and second order. Both the conditions of KKT will be considered to be discussed for the optimality of a constraint optimization problem. Well, I stop here. Thank you. Thank you all for all of your presence.